Okay, so this is the topic, fatigue failure topic. Fatigue is a very important phenomena for the failure of material. It is actually the failure under lengthy period of repeated stress or strain cycling. So that means uh, if the load on the material is being applied on a repetitive basis, for example, on the bridges. So uh, generally you can see that the buses or cars are passing by on the bridge. So these constant flow of buses and the traffic on the bridge cause repeated loads on the bridge. So therefore, the bridge is subject to constant repeated stresses and strain cycling. So we can model these stress and stress cycles in a number of ways that we will see later on. So the stress on the so when we model these stresses in the case of the fatigue loading, then we assume that the stress varies with time, and then we assume certain type of variation of the stress with the time. So in those situations, the key parameters for the failure, for the fatigue failure, are the number of cycles and the uh, average of the stress and the level of stress S. So therefore, we need to consider these factors. So what are the key points in fatigue? As I have just mentioned, that it is a very important type of failure, and most of the failures for the mechanical parts result from the fatigue phenomena. Okay, at least 90% of the mechanical engineering failures uh, are due to fatigue. And in this fatigue failure, normally when you apply a load on the material, when the load on the material is increased up to its yield strength, then uh, the stress on the material increase up to the yield strength, then there is a failure. But in this case, since the load is applied on a repeated basis, there is of course no need for the load to be up to yield strength. So maybe half the yield strength or 60% of the yield strength load, when it is applied repeatedly, maybe thousands or millions of times, then uh, the failure in the material can take place. So for the fatigue failure, generally an apparatus is used in which a specimen is placed in that apparatus, and that specimen then applies repeated loads. So for example, uh, uh, this specimen over here is deformed in such a way that a repeated actions of compressions and tensions are applied uh, repeatedly. So this is the schematic diagram for an application for the performing rotating bending fatigue test. So it is a fatigue test can be performed for pure tensile and compressive cycles as well, but it is more easy to perform a, a bending fatigue test. In the bending fatigue test, when this rod is bent from the two ends, then compressive and tensile stresses are produced. So for example, at the bottom there will be compressive stress, at the top there will be at the bottom there will be tensile stresses, at the top there will be compressive stresses, and these will keep rotate these will be applied on a repetitive basis. So for a proper application and the a simulation of the fatigue failure. So you may view certain videos about the fatigue failure test on YouTube. Okay, so now let's talk about the loads which are applied on the in the case of fatigue. So these loads are cyclic in nature. So first kind of load is this. So in this case, you can see that the load or the stress increases to some certain value, then it decreases back, and then it decreases again to the other side, to the negative side. So that means if in the first cycle, both the tensile and the compressive stresses are applied, and these are applied in such a way that the maximum tensile stress is equal to the maximum compressive stress. Therefore their average will be 0. Okay, their average mean stress will be 0. And later on we will define about some of the expressions about the average and the range of stresses in this case. So this is the first option or first case for the cyclic stresses. In the second case of cyclic stresses, in the case of fatigue, the stress cycle also changes from tensile to compressive regions. But in those situations, the tensile or the compressive stresses, maximum tensile or maximum compressive stresses will not be equal to each other. There will be that means the mean value of the tensile and the compressive stresses will not be 0. So as in this case, you can see that this type of stress cycle is more toward tensile stresses, and the mean value is this much value. There's this mean value about some value in the tensile region. Okay, so the other options in this stress cycle are also apparent from here. That means the total range of the stress, okay, total range of the stress is from here to here, which is equal to sigma maximum and then plus this negative value. And the amplitude, so this is another quantity over here which is called as the amplitude. Amplitude is can also be determined. Amplitude is the this is the sigma a. So this is the stress amplitude, which is basically half the value of the this stress range. And corresponding to these values, we can write these following equations. So the mean value is sigma max plus sigma minimum divided by 2. Okay, remember that and then sigma r range is sigma max minus sigma minimum, and stress amplitude is equal to sigma r divided by 2, or in terms of sigma max minus sigma minimum divided by 2. Remember that when, for example, sigma max is the tensile stress and sigma minimum is the compressive stress, so here we will use a negative value over here. So for example, if sigma max is 50, sigma minimum is 20 compressive stress, so it will be 50 plus, and then 20 will be compressive strength, so it will be minus value. So it will be 50 minus 50 minus 2. That means it is 30 divided by 2 is 15. So mean value will be 15 in this case. However, the range of value will be 50 minus 20. 50 plus 20, that will be 70, and then the amplitude will be 30 in this case. So So that means, in summary, what you can say that tensile stresses will be put as positive values, and the compressive stresses will be put as negative values into these equations. And the third type of case is just the irregular application of the stress, both in terms of the stress magnitudes and their frequency. There is no further discussion about this cyclic stresses over here, but most interesting cases are these first two cases for the discussion of the cyclic stresses. Okay, so what are the types of fatigue behavior? The meaning is that, for example, if there is a materials, there is a metal or some alloy, so how that metal will behave under the fatigue load. So there are actually two types of behaviors which are shown over here in these two graphs. So in this first graph, as you can see that the graph is between the stress amplitude and the number of cycles to the failure. So for example, if I take some value over here and then I draw a horizontal line up to this, and then the corresponding number of cycles to failure will show. So for example, if I have this stress value, that means, I don't know, maybe 200 megapascal. At 200 megapascal, it may fail for like 10 to the power 5 cycles. So it's like that. So as you can see that if this stress amplitude is decreased, in this case, the number of cycles needed for the sample to fail will increase. Okay, so this kind of behavior is observed. So it is obvious that the stress magnitude of the stress is decreasing, so it will take more number of cycles to decrease. But below certain number of certain value of the stress, we will see no such failure in those cases. So in this case, this kind of material will exhibit a value which will be called as failure limit. Okay, so this will be called as a failure limit value. Okay, so there are two types of fatigue behavior observed. So one is the fatigue limit. So it is the fatigue limit, not the failure limit. So in this case, there will be no fatigue if this applied stress is less than the SFAT, F fatigue. So for some material, there is no fatigue limit as well, but this is over here. Okay, so the example is for the example for the first case is typically steel is such a material. Okay, and the example for the second kind of material, in this case, there is a continuous decrease in the stress until certain practical values, and in this case you can see that although there is a decrease in the stress, but there will be a number at which there will be a failure. So although that number will be a number of cycles needed will be much higher, but in this case the failure will in any case will take place. So this is the this occurs in the case of aluminium. So we can also define the fatigue life. It is the total number of cycles to cause the fatigue failure at a specified stress amplitude. So you can find the fatigue life from the x-axis, and then we can find the fatigue limit from the y-axis. And these types of charts are normally called as the SN charts, and in which on the vertical axis stresses are shown, and on the horizontal axis a number of cycles to failure are shown, often on the logarithmic scale. Okay, so this is almost the end of this video clip, so we will continue this topic in the next clip.